Okay, let's start. Uh, yeah. So, hi everyone. Welcome back to the last session of this masterclass. Uh, for for the people who were asking for the data set and the resources, so we have already shared the slides and the codes. We will share the data sets by today. Uh, I think we only have people who were there in the last two sessions, so no need for any introductions. So I think we can just start.
Okay. I think my voice is clear, right?
Yeah.
Okay, let's start. My screen is visible now.
Yeah.
So, guys, in the past two sessions, we have discussed a lot of things related to simple linear regression, multiple linear regression, especially saw how do we write the model, how do we estimate the beta, what are the assumptions, actually, how do we implement those things in Python, see the summary, how do we identify if the variable is significant or not, and how do we interpret R square, adjusted R square, how do we interpret root mean square, mean square, predict on the test data, and overall make our final model. But in this session we are going to deep dive into the hypothesis testing in regression, especially the one of the thing that I explained you earlier. So let me just show you one more slide. Give me one second. So if you can see my screen, earlier we had seen how do we interpret the hypothesis testing test related result. Once we let me run the code once. Yeah. So just give it a second. Yeah, we saw this particular thing like when we do the linear regression using the stat models library. So stat model is one of the library in Python, which is basically for a statistical analysis or a statistical library. It gives you more information about statistical information about any particular thing. In this model you also find implementation of time series analysis, regression, and all those things. So here you can see that you have a p-value thing, and based on the p-value, we actually told if this p-value is less than 0.05, then we say that our regression coefficient is significant. So in this manner, you can see that this particular these four regression coefficient are not actually significant, and this is why we are going to deep dive into how we construct this hypothesis. Okay, so if we just go into the one of the important questions in the regression is like, let's say we fit a regression model, we have p predictor variables. So one, those who are new, predictor
I think Nitin lost his connection.
So
Uh, can someone tell if I am audible and visible?
yeah, you are audible. My voice is audible, right?
Okay. Yeah.
So sorry, I got disconnected. So I was telling about this particular predictive variable. So let's say we fit a model and we want to see if out of these predictive variables, are there any particular x or fall into the y or z variable. So how do we do that? So for that particular thing, we can utilize the concept of hypothesis. So what we are going to do, so we will just start by basic. So let's say for any particular predictive variable xj, the estimated coefficient is bj. So this beta j or this particular thing is the estimated coefficient for xj. So what we want to do, let's say we want to test a hypothesis or for some individual coefficient of regression. So it's about xj, any particular coefficient we are talking about. So xj अगर कोई predictive variable है तो उसके corresponding जो estimate है beta j, we are only talking about testing regression coefficient. So let's say we have a value which is beta. Beta say 10, let's say. So we want to check whether our beta or not. So this is this is whenever this is not true, the second thing is going to be called of predictive variable xj is equal to beta j naught. So beta j naught can be any number. So this is a number, but this is our estimated what you can estimated coefficient that we want to test. So the null hypothesis here
Nitin,
is that yeah.
can you also record this on your computer? I think my connection is also unstable. You can also start recording or start recording on your computer. Did you find it?
I was telling, let's say, yeah, it started.
Okay.
So I was telling, let's say beta j is equal to beta j naught is the hypothesis that we want to test. Then our null hypothesis is beta j is equal to beta j naught, and our alternative hypothesis is which is not equal to beta j naught. So alternative hypothesis in general can be of three types. Like this is one of the alternative hypothesis. Other can be like beta j greater than beta j naught, and other thing like beta j beta j naught. So these three particular hypotheses can be possible. But in this case, we want to test where your coefficient is equal to some predefined number or not. So this is what your hypothesis is going to be. Now once we move ahead, we have certain things that you calculated in our regression coefficient. So what we have, so earlier I told you like the error terms in the regression coefficient follow 0 comma sigma square. Okay, so this is just one of the general assumptions. So like once you calculate the estimate the beta hat actually follow normal distribution. So you may assume why we have termed as normal p plus 1. So this is actually multivariate normal distribution. So without going into much of the explanation of what is multivariate normal distribution, just assume that we have here a beta hat is equal to beta naught hat, beta 1 hat, similarly beta p hat. So we have here p plus 1 coefficient of regression, and all those follow normal distribution. So collectively we can represent everything in the single representation of normal distribution. So we can say that beta naught follow normal distribution, beta 1 follow normal distribution, beta 2 had follow normal distribution. We collectively say that beta had follow multivariate normal distribution. So this particular thing is the mean, and this second thing is called the standard deviation. This is mu comma sigma square. So this is called variance and this is called mean. So this whole thing is just one of the calculation that we get once we estimate our beta from the method of least square. So this particular thing is information that we are going to utilize for making our test statistics. So what is this particular thing? This particular thing says that your beta hat, which is actually the vector of beta naught to beta p, and there are p plus 1 betas there, which actually follow normal multivariate normal distribution with mean beta and covariance. This particular quantity is called the covariance. Sorry, the variance. Okay. So talking about their particular test statistics. So let's say we denote this X transpose X inverse by the quantity C ij. So, like this X transpose X inverse is just not a single quantity. It is going to be a matrix. Okay. So this matrix will have some this particular thing. So let's say this is the X transpose X inverse. So without going into like how do we calculate X transpose X inverse, we can easily calculate using the any software or manually also if the data is not large. So our test statistic minus divided by this is called the standard error of beta. So
So
this is
what
called
is the test statistic here? What does it
test.
mean?
So test statistics actually is a quantity based on which we test whether our null hypothesis is true or not. So we actually make test statistics based on the assumptions of null hypothesis. So specifically I told ki our null hypothesis is beta j is equal to beta j naught. So based on this particular thing, we actually assume that if the beta j follow normal distribution with a mean beta j and beta j hat, and this particular thing as the variance, then based on that we make a test statistics. So this test
So
statistics
is
will give us
this
the,
is
yeah.
this like the p-value?
Exactly, it's we will use this to calculate the p-value, but test statistics is just you can say that it's a number on which we will calculate the, on the basis of which we will calculate the p-value. So this particular thing is based on whatever information we have about the beta, like the information of the distribution about the beta. So we know that our beta, specifically for any beta j follow normal distribution with a mean of beta j hat sorry this beta j and X transpose X inverse sigma square, this particular thing will be called as its variance. So this particular information we are utilizing for calculating our test statistics.
We have a question from Tushar. Can you please explain from where this predefined number came?
So
Which
okay,
predefined number?
yeah, I will explain this predefined number later in this particular slide only. So just for the assumptions, assume that this particular beta j hat is a predefined just this slide. So in general, this is what we have as when tj means this is for the coefficient beta j. Now one more thing, like in the real life sigma square we don't know, because when you collect the data, we have the data of let's say 1000 we have 1000 rows in our data. Based on that we don't know what is the what is the sigma square of population. We only have the test data of like a sample of 1000 data. Okay, so based on that we actually use mean square error as the what you can say unbiased estimate of sigma square. So this MAC is called unbiased estimate of sigma square. So you can see here that we have used here sigma square, but we have not used here sigma square. We have used here mean square error. So this mean square error is actually the unbiased estimate of sigma square that we use. So because in going to be, so we only have what we can say variance from the test data, and this is what we are going to use. So overall the main idea is we know the distribution of beta hat, and based on Okay, and P is the number of columns and -1. So this is the T distributions that TJ is going to follow. So N is the total row and P is the total number of columns. So let's say in we have 1,000 rows. So N is equal to, let's say, 1,000, and let's say P is equal to 5 columns. Then your T distribution is going to be 1,000 minus 5 minus 1. So this is going to be 994. So this is a degree of freedom for that particular T distribution. Obviously, also I told that this particular under root MSE upon CJJ is called a standard beta. So test statistics in general means that whatever you want to test minus whatever predefined number you have by a standard error of beta j. So if you don't want to go into the complex mathematical term, simply say that beta j minus the number that you want to test upon a standard error of beta j. So this standard error you always get, like also I so you can see that here we have the standard error, and this is what standard error I mean. So basically, let's say want to test if BMI is equal to 340 or not. So write BMI minus 340 upon standard error of BMI that we get from the calculation. So this particular formula, this here is called the BMI of the standard error, the standard error of this particular columns you can get here. So this is what an overall idea from that particular thing is. So once again we can start the slide. Let me just start the slide also. So once we have this particular thing, we can calculate the p-value, and if the p-value is, let's say, we know that we have our this tj actually follow the in t distribution with n minus p minus 1 degree of freedom, and based on that we can calculate the p-value. If p-value is less than 0.05, so p-value is less than 0.05 means that our h naught is, so let me go back and show how, so you what our h naught was. So okay, so let's say if we have p-value of less than 0.05, so we can say that this particular h naught is not beta. Now say that
Nitin, I
our
think we are
alternative
having
hypothesis
some
is
disturbances in the video. Let's do one thing. Maybe let's turn off our both of our videos.
yeah,
Let's just
yeah.
stick to audio. Yeah.
Yeah, definitely. So if your p value is less than 0.05, in general we can say that uh, your h naught is rejected, or h naught is not accepted. So in this particular case we'll have beta j not equal to beta j naught. Now someone asked me, if let's say we do all these things, then what is the how this beta j not coming into the picture? How do we actually define this predefined number? So this particular explanation that I gave you, it was a very general explanation of how we do hypothesis testing, but this is not an ideal way. So what is the ideal way? Generally we want whether our regression coefficient is significant or not. So significant, what does this significance means? So let's say we calculated beta j, we want to test whether this particular things in existence had some what we can say, some value in predicting y or not. So how do we do that? Let's say we defined beta j naught is equal to 0. So in that particular case our hypothesis testing becomes beta j is equal to 0 and beta j not equal to 0 is the alternative hypothesis. So in this particular case, let's say if h naught is rejected, it means that your beta j is not equal to 0. It means that whatever estimate that you have got for the beta, it is actually significant. Whatever the estimate that you have, it is not equal to 0, and it had some significance in predicting the y. So that is why we started with the general of beta j naught, and we actually concluded here with the beta j naught equal to 0. So when you want to test the, just give me, let me
Nitin, we can't hear you. Let's wait for Nitin to join back. Nitin is just joining back in 2 minutes. Okay, Nitin's here.
Yeah, yeah.
Try
I
Nitin.
cannot share the screen.
Just a minute. Yeah, try now.
Yeah. Guys, really sorry. My internet connection is not stable today. So screen is visible, right?
Yes.
Okay, so this I was telling ki when you will replace beta j naught by the zero, it simply means that we are testing our regression coefficient is significant or not. And basically, this is what we usually get when we try to implement this hypothesis testing in this stat model library. So let me, once you get the intuition, let me give you how this things looks like in practical. And actually I have also explained this particular thing in earlier sessions, and we have seen this particular thing, but yeah, the intuition was missing, and I think we have given you the intuition of how the things are happening. So once you implement this particular hypothesis testing, you can here see that we get a lot of p values here. So, and this is what the T means, that it follow the T distribution, and we can also call it a T statistics or whatever you want to say. But yeah, TJ in general means that we are talking about the jth coefficient or jth predictor variables. So whether when you find that key, whether your your p value is not less than 0.05, what you can see, you can actually delete all those predictor variables, and you are going to get the same value of adjusted r square and r square. So let me just explain it with the this similar thing. So what we are doing, we are here deleting all those predictor variables which are not significant. So here you can see that this south region southwest, or region southeast, region northwest, and this particular 6 mil that we have seen here, these are all not significant. We are going to delete all these things, and let's see how your r square and adjusted r square are going to look. So once we delete this and again fit the model, you can see that based on all these remaining features or predictor variables which are highly significant, everyone is highly significant, you can see that you are going to get the same or similar r square, adjusted r square. So this is what this particular things means in general. If you want to test the significance of a particular predictor variables, it means that you have to calculate the tj, which is equal to beta j minus 0 upon a standard error of beta j. And this particular things will follow t distribution with n minus p minus 1 degree of freedom. And once you calculate this particular thing, check the p value. If the p value is less than 0.05, you can assume that this particular thing is significant, otherwise it is not. And this is based on the alternate null hypothesis that beta j is equal to 0, and alternative hypothesis that beta j not equal to 0. So this is what
So,
overall things looks like as a whole.
so basically, stat model does everything in the background.
Yeah,
It
it
calculates
gives,
the
yeah,
TJ
yeah.
and everything, and directly gives us the p value, and we can directly filter out the columns based on whatever our p value threshold is, and we can remove those columns, and yeah, that's it.
Yeah, so this is what how the procedure looks like. So this is the hypothesis testing that you make. Hypothesis, this is the TJ that you make. Then this is the distribution that they follow, and this is the decision that you make to based on the p-value. So this we do to test the individual significance of regression coefficient. Individual means we are checking for jth coefficient. So यहाँ पे हमने देखा कि जो जी फोर चार वेरिएबल्स हैं significant नहीं है, we actually deleted those. But there is some other kind of hypothesis testing in the regression where जहाँ पे we test overall significance of model. So this is called overall significance of model. So let's say your significance of model. So let's say your model has, let's say this particular model has, I think 1 2 3 4 5 6 7 8 7 or 8 variables. Okay, but you can see that 4 variables are not significant here, but it cannot these variables are not significant, and if you are going to remove those variables, we are going to still get the same p value and sorry, same r square adjusted r square that you have got here. But the thing is that this model as a whole is significant or not. I'm not talking about any particular individual coefficient, but we're talking about model as a whole, like taking all the predictor variable into consideration, whether this particular thing is significant or not. So for that particular thing, we use if test. So I'm going to give you a small glimpse of that also, but let me give you how that particular things looks in this particular example. So you can see here that we have got the if statistics. So this if statistics is based on the fact that whether your model is significant or model as a whole, I'm not talking about any individual coefficient, is significant or not. So here
So
you can get the
what
if
what
statistics.
does it mean? What does it mean for a model to be significant or not significant?
Yeah, so it means that let's say here you can see that your model has 8 variables. Okay, out of it 4 variables are not significant. But if even if we use this whole model to predict something, and our model is significant, this means that these 4 variables which are not significant is not going to cause you any problem. So अगर यहाँ पे आप 4 variables को consider करते हैं, क्योंकि आपका model overall significant है, you are still going to get the same value of predictions result and all those things. So because your model as a whole is significant. So यहाँ बहुत बार ऐसा होता है कि your these 4 predictive variables are not significant and your model as a whole is also not significant. It means that your model is not able to give you or you can alternatively you can say that your model is not able to explain or the R square, adjusted R square about the model. These all things are not valid, or you can say these are not significant at all. So let's say your model gives you R square of 0.201. So it means that key out whether when you are trying to use all the predictor variables and you are still getting very low R square, it means that there is some problem with your model. So वहाँ पे if you will test the significance of your model, you will actually get that your model is not significant as a whole. We are not talking about the individual regression coefficient. We are talking about the model as a whole. So when you will let me show you how this particular things looks like, and then I think this particular thing will be more clear. So we'll also see like how do we you can say how do we actually construct the hypothesis for that particular thing. My screen once again. Yeah, so once we move ahead, we want to test the overall significance of regression model. So one natural question is, okay, what is going to be the hypothesis in this particular case? So overall significance of model कहने का मतलब ये है कि आपका जो overall ये model significant यहाँ पे जो hypothesis होता है वो ये होता है कि all your betas like beta 1 beta 2 whatever your betas are, all your betas are actually equal to 0. So this is the combined hypothesis testing that we are actually doing for each and every model, combined hypothesis testing. So यहाँ पे if we check that we have alternate null hypothesis as beta 2 beta 3 and similarly beta k equal to 0. So this is the combined hypothesis for all betas. And we are combinedly checking this particular thing, not individually. Individually ये significant हो भी सकते हैं, नहीं भी हो सकते हैं, but as a whole, like taking everything in consideration, are they significant or not, that you want to test. And the null hypothesis यहाँ पे होगा कि अगर यहाँ पे एक भी ऐसा वेरिएबल है जो significant है, then we actually say that कि our regression model is significant. So our H1 is not all slope coefficient are simultaneously 0. It means that there exists some beta, let's say beta k, which is not equal to 0. तो अगर आपका सारा का सारा बीटास जो है अगर 0 की इक्विवेलेंट है, नॉट सिग्निफिकेंट है, तो वहां पर आपका मॉडल भी सिग्निफिकेंट नहीं होगा. एंड दैट इज व्हाट वी चेक as a whole. So before doing the hypothesis testing, we actually check if our model is significant or not. अगर आपका मॉडल is significant नहीं है, then there is no point in considering checking individual coefficient significance. तो पहले हम लोग चेक करते हैं कि मॉडल हमारा सिग्निफिकेंट है कि नहीं. देन वी गो फॉर चेकिंग आउट ऑफ दिस सिग्निफिकेंट मॉडल विच ऑफ दिस वेरिएबल्स आर नॉट सिग्निफिकेंट. सो अगर यहाँ पे एक भी वेरिएबल ऐसा है विच इज नॉट इक्वल टू 0, इट मीन्स दैट वी हैव our model as significant. So this is pretty much straightforward. H0 is that all the betas are 0 and H1 is at least one beta. एक कोई ऐसा betas है like beta k, beta p कुछ भी हो सकता है which is not equal to 0. So in that particular case, our F test, or you can say that F statistics is this is ESS, or you can say that we have residual sum of square. We call it RSS also, or SSR also. There is multiple name. So ESS mainly means that error sum of square, and we also call it SSR or sum square due to SSE, sum of square due to error. Same thing. These are all having the different notation. And this is RSS as residual sum of square. So this particular ratio will give you F statistics, and that we also will see in the code. And based on that, you calculate p value. If this p value is less than 0.05, you actually say that your this null hypothesis is rejected, and at least one of the beta is there that is actually not equal to 0. So overall, what we do, we check this particular thing based on the error sum of square and residual sum of square that we also saw earlier in the masterclass.
So we calculate another p-value from the F statistics.
Yeah. This is for the whole model, like starting from all the betas. And so, like checking this all thing in order, what we do, first we check this significance, and let's our model is significant. Then we go for individual testing and remove all those variables which are not significant.
And we have some questions. What were N and P? So N, I think, was the number of rows.
Rows, yeah.
And P is the number of columns. Can we check whether the model is significant or not using forward selection, backward elimination?
Okay, so in variable selection, I think some people are confused with the variable selection. So fundamental of variables, which I am not going to explain everything here. So what we do there, let's say at a particular time point t, what we have two model, M1 and M2. So we want to test whether M1 is better model or M2 is better model based on the all the predictive variables present in M1 and all the predictive variables present in M2. So in that particular case, we also apply F test there. Like we have some different form of F test, but yeah, we apply F test there, and out of those, we are able to check whether M2 is better model or M1 is better model. But yeah, this particular thing, I'm not talking about a variable selection. I am talking if we have a model, let's say M, you want to check whether this M is overall significant or not, then what you need to do. So variable selection is not about finding the like checking whether the model is significant or not. Variable selection is about finding the most what you can say most most matlab, all those number of variables. So let's say you have find subset of this p variable, let's say r, which is less than p. So out that those r variables can explain the models equally like the p variables can explain. So that is about finding a subset of predictive variables that can explain the model equally when you are actually trying to use all the predictive variables. So let's say अगर आपके पास model में 100 predictive variables हैं and you are come up with r is equal to 20 that can explain the models equally. So यहाँ पे r is equal to 20 will be preferred because this will make your model simpler. अब अगर आप फर्दर एनालिसिस के लिए जाओगे तो वो 20 वेरिएबल्स आप सिंपली फील कर सकते हो, आप उस पर कोई अदर टेस्ट कैरी आउट कर सकते हो, उस पर उसको आप मतलब रियल लाइफ में अपने डेटा में और उसको इंटरप्रेट कर सकते हो rather than interpreting 100 variable at once. So variable selection is about finding a subset of variables, but yeah, the overall thing is that there you also use F test to find which of the particular model out of all those possible is better. But this is the general concept behind the test for significance of regression.
Then we have another question. How do you test significance of tree-based models?
So actually in this lecture, we are not considering about the tree-based model. We are only considering about linear regression. But tree-based models are one, first of all, not a parametric-based model. They are non-parametric. So we don't make any assumptions or any assumptions of distribution of the model. So in that particular thing, I think it is overall not required, or it's there. If you, let's say, अगर आप करना चाहते ही हो, then you can go for some non-parametric test, which I think at this point is uh, like out of scope for you.
Yeah. There's one interesting question which I also have. Can't we do the t-tests for all the predictor variables instead of this F test for the whole model?
Okay, so like t-test, we don't means t-test is used for calculating the or comparing like a single variable. So let's say we have let me give you a simple intuition behind this particular test. So this is the test coming from the statistics. So let's say we have a data x1, a random variable x1. We want to check whether this particular x, let's say x bar is equal to some particular mean, let's say 20. Once I mean 20 but let's say we have x1 to, let's say, x10, and we want to check for all this particular thing whether x1 is equal to 10, x2 is equal to 20, x3 is equal to similarly. So for this thing we cannot use t-test. Like t-test is uh, uh, have the limitation that we can test for only some particular number of random variables, not for all at once. So that is why this f test is coming into the picture. So अगर आप individually भी टेस्ट करते हो, तो लेट्स से अगर आपके पास 1000 प्रिडिक्टिव वेरिएबल्स हैं, तो आप 1000 बार टी टेस्ट करोगे इंडिविजुअली सबके लिए, तब आप उसमें से वो सारे वेरिएबल, लेट्स से 500 वेरिएबल सिग्निफिकेंट नहीं है, यू विल बी एबल टू रिमूव. बट हम लोग पहले क्या करते हैं कि पहले देखते हैं कि हमारा मॉडल सिग्निफिकेंट है कि नहीं. अगर आपका मॉडल सिग्निफिकेंट नहीं है, अगर आप उस 500 वेरिएबल्स को हटा भी देते हो, देन इट इज नॉट गोइंग टू बी एनी यूजफुल फॉर यू. तो फर्स्ट ऑफ ऑल वी चेक आवर मॉडल इज सिग्निफिकेंट और नॉट. सो एक बस सिंपल टेस्ट से हमें पता चल जाएगा, हमें 1000 वेरिएबल के लिए इंडिविजुअली टेस्ट करने की जरूरत नहीं है. एंड वंस यू फाइंड कि अच्छा मॉडल इज सिग्निफिकेंट, देन इट मीन्स दैट कि कोई तो ऐसा बीटा है जो कि 0 के इक्वल नहीं है. So in that case, what you can do, you can go for individual hypothesis testing and start removing all those variables which are not significant.
Got it. Then, so where you put variable selection methods before hypothesis testing or after that? When do we
So
do variable selection? Yeah.
we generally do variable selection, means you can do it before also और after also. अगर आप पहले करोगे तो ये सारे वेरिएबल सिग्निफिकेंट नहीं है, वो तो हट ही जाएंगे, और भी कुछ वेरिएबल्स हट जाएंगे जो कि ज्यादा यूजफुल नहीं हो रहे हैं. बट आफ्टर द दैट वी यूज लाइक वंस आवर मॉडल हैव ऑल द सिग्निफिकेंट वेरिएबल, देन वी अप्लाई वेरिएबल सिलेक्शन मेथड. बिकॉज अगर आपके पास इनसिग्निफिकेंट वेरिएबल्स हैं तो वो तो कोई पॉइंट ही नहीं है रखने का ना. इट विल नॉट कंट्रीब्यूट एनीथिंग टू योर व्हाट यू कैन से this particular thing. So we do have the variable selection before also. उसका कुछ concept अलग है, मतलब उसका interpretation अलग तरीके से होगा. But if you do it after the hypothesis testing, उसका interpretation अलग तरीके से होगा. So let me give you one basic example. So let's say your predicted variables x1, x2 and x3 are there. So ऐसा हो सकता है कि x1 और x2 अगर हम सिर्फ मॉडल में यूज कर रहे हैं y को प्रिडिक्ट करने के लिए, तो ये दोनों सिग्निफिकेंट हो, एंड अगर x3 यहाँ पे आ जाए तो यहाँ पे x2 इनसिग्निफिकेंट हो जाए, तो वहां पे एक मॉडल का सिग्निफिकेंस और एक वेरिएबल का सिग्निफिकेंस ओवरऑल इतने उसमें वेरिएबल प्रेजेंट है उस पर भी डिपेंड करता है, बिकॉज दिस बीटास विल बी एस्टिमेटेड अकॉर्डिंगली. So if we'll go into the deep and study the different combinations of random variables, the predictor variables in the regression, you can say that अगर ऐसा हो सकता है कि अगर x1 x2 let's say साथ में दोनों significant है, ये भी significant है ये भी, and you just bring out some new random variable x3 predictor variables and then you again fit the model, ऐसा हो सकता है कि इसके प्रेजेंस में इनमें से कोई एक इनसिग्निफिकेंट हो जाए. So that can also be possible. So अगर आप हाइपोथेसिस टेस्टिंग पहले करते हो तो आप ये चीज फिल्टर आउट कर सकते हो. तो वहां पे आपको जो नंबर ऑफ प्रिडिक्टर वेरिएबल्स मिलेंगे, लेट्स से r लेस देन n एंड p, वो अलग अलग मिलेंगे जो आप प्रिडिक्टर हाइपोथेसिस टेस्टिंग के बाद करते हो. So these things are there in the, if you just go and read any textbook for the regression, these things you will find.
I think that's all for the questions yet. We can move ahead.
Yeah, so I just let me show you for once the if test in the code, and then I think we'll move the multi-quantity and studied spacing. So let me share the screen once more. So here you can see that we have got here our if test as this particular quantity. So if statistics का मतलब होता है कि जितना ये हाई रहेगा, that is more better. So यहाँ पे आप देख सकते हो कि probability of statistics is 1.05 into 10 to the power minus 288, which is highly zero. So this is equal to approximately zero. So this means that your model is like overall highly significant. And this particular thing we do because अभी इंडिविजुअल कोफिशिएंट हमें दिख रहा है बिकॉज आवर मॉडल इज वेरी स्मॉल, बट लेट्स योर मॉडल हैज 300 400 वेरिएबल्स. वहां पे आप पहले देखोगे कि योर मॉडल इज होल सिग्निफिकेंट और नॉट, एंड देन यू विल गो फॉर दिस पर्टिकुलर इंडिविजुअल एनालिसिस एंड रिमूविंग द वेरिएबल्स.
I hope everyone understands what exactly is p-value. If not, please ask in the chat. Let's move ahead until then.
Okay, so now for the last topic of the session, we will start with the multicollinearity, and let me just have the slide here. Okay, so once we have discussed the hypothesis testing, we have find out all our significant variables. Then one more thing that has means the problem can be with the model is the multicollinearity. So how this multicollinearity starts? So like in the initial classes we actually had the assumptions of the regression, and in the assumptions of regression we had a very basic assumptions that there should be no linear relationship among the predictor variables, or it is also called no multicollinearity. So this particular thing is also termed this way. So अगर आपके पास जो भी प्रिडिक्टिव वेरिएबल्स हैं उसमें अगर आपस में लीनियर रिलेशनशिप बन रहा है, लेट्स से x1 to xp आपके पास p प्रिडिक्टिव वेरिएबल्स हैं, लेट्स से x2 और लेट्स से अल्फा टाइम x2 प्लस अल्फा 1 टाइम x2 प्लस अल्फा 2 टाइम्स x3 मिलके x5 को predict कर रहा है, it means that there is some linear relationship among the x5. It's not about two variables, it can be any number of variables. Let's say alpha 1 x1 plus alpha 2 x5 plus alpha 7 x7, something like that मिलके, these alpha are just the number, this is not, you can give anything, किसी x9 को predict कर रहा है. So उनके आपस में ही कुछ लीनियर रिलेशनशिप बन रहे हैं. सो दिस इज एक्चुअली प्रॉब्लमेटिक फॉर योर मॉडल, बिकॉज इन दैट केस जो हमने बीटा हेड का एजम्पशंस बताया था उस टाइम, एस्टिमेट कि एक्स ट्रांसपोज एक्स इनवर्स एक्स ट्रांसपोज वाई, दिस पर्टिकुलर इनवर्स एक्चुअली हैव प्रॉब्लम, ये एग्जिस्ट नहीं करता है, या फिर ये एक स्यूडो इनवर्स में निकालना पड़ता है. सो दैट इज नॉट एक्चुअली is going to give you the actual estimate of beta. So multi-quality
Also,
तब, yeah.
does that linear relation need to be exact, or can it be like approximate as well, like
Yeah,
alpha
it
1
can be
x1?
approximated. So like in linear regression term, there is two things that we call. There is we called exact linear relationship, and we called near linear relationship. So exact linear or near linear. So this near linear, exact linear can be confusing, but overall, some assume that exact means ki we have a very strong relationship, and near linear means we don't have very strong, but yeah, we or near linear relationship. So I think that is what you wanted to say.
So, so that near linear will also be called multicollinearity.
Yeah, it will come. It will not have much effect, but it will have the impact on the regression coefficient.
Hmm.
It will have some impact. But yeah,
But
this
the
exact linear
inverse
have
will
more impact.
still exist, but
Yeah,
it will have
inverse
some
will exist,
impact.
but exact linear के case में it may happens that the in pseudo once inverse does not exist, we may go with the pseudo inverse, and that is also the case with the near linear. And यहाँ पे होता है ऐसा है कि अगर आपके पास exact linear होता है तो वहाँ that is highly unreliable rather than the near linear. वहाँ पे थोड़ा बहुत rely कर सकते हैं, but it will also impact the coefficient.
Hmm.
So one more thing is like, and this is also the one of the interview questions, like what is the consequence of multi-quality. So यहाँ पे हम लोग very basically समझेंगे कि multi-quality केस में first of all क्या होता है कि जो least square estimate है वो hold नहीं करता. Like जो हम लोग ने बोला था बीटा इट इज इक्वल टू एक्स ट्रांसपोज एक्स इनवर्स एक्स ट्रांसपोज वाई, ये हमने जिस एजम्पशन पे बनाया था, तो हमारे एजम्पशंस क्या थे कि वहां पे मल्टी-क्वालिटी नहीं होनी चाहिए. सो इफ यू हैव द मल्टी-क्वालिटी, इफ द प्रेडिक्टर वेरिएबल्स आर correlated among themselves or having some linear relationship, then वहां this is not true, or you can say that this does not hold. So problem क्या होती है? The problem is this least square estimate and their variances. So we told कि हम लोग बीटा हेड और उसके स्टैंडर्ड एरर वेरिएंस भी कैलकुलेट कर सकते हैं. So these all becomes very large because this inverse itself is the problem. So that is why these estimates and their variances becomes very large. तो वहां पे जो आप प्रिडिक्शंस करने वाले हो, जो वहां पे आप हाइपोथेसिस टेस्टिंग करने वाले हो, that will be actually going to be misleading because your estimator itself is not a good estimate of the what you want to estimate. So in that case your whole assumptions is uh, violated. In that case your whole analysis after that is going to be misleading. So यहाँ पे हमें इसको हैंडल करना पड़ेगा. पहले तो आइडेंटिफाई करेंगे, then we'll try to see how do we handle it. So these particular two things is there. Least square estimator does not hold, and the second thing is there. What's the main problem? Main problem is their variance and the estimator. Whatever the estimator like this beta j hat, beta 1 hat, all these beta hat estimated are actually becomes very large. So वहाँ पे what we do, the first thing is that how do we detect the multi-quality. So one basic criteria is that before detecting the multi-quality, first we need to center and scale the response and predictor variables. तो वहाँ पे हमें ये जो data है उसको scale करना थोड़ा जरूरी है, because once we scale the this particular thing, it will be easy for us to make the calculations based on the variance inflation factor. So why do we do that? So we do that for this particular thing. So this variance inflation factor is the main cause or main what you can say main metric that we actually calculate to find whether there is a multicollinearity in your data or not. So variance inflation factor VIF, which is again the one of the most asked questions in the regression or data science interview. So let's understand how do we calculate this variance inflation factor. So let's assume that you have x1 to xp amount of predictor variables. We are still not talking about y here. y is still not in the picture. Now what we want to do, let's say at any particular time point we are considering about variable xi. Out of these x1 to xp, we regress xi with remaining predictor variables. So how, what are the remaining predictor variables? x1, x2, xi minus 1, xi plus 1 डॉट xp. So यहाँ पे xi नहीं है, बस xi को हम बाकी predictor variable के साथ क्या कर रहे हैं, रिग्रेस करा रहे हैं. So अगर p predictor variables है, then we have here p minus 1 predictor variables. So वहां पे ये xi यहाँ पे y की तरह एक्ट करेगा, एंड y के बारे में अभी बात नहीं करें, वी आर जस्ट टॉकिंग अबाउट predictor variables. एंड बाकी predictor variables को हम लोग एज ए x की तरह ट्रीट कर रहे हैं. Then in that particular case we will get some r square, just denote as r square xi. यहाँ पे हम r square xi से डिनोट कर रहे हैं because we are considering xi as the y variable. अगर आप x2 कर रहे हैं तो r square x2 बोल सकते हो, आप r square x5 बोल सकते हो. Now what we have to do, we have to calculate this VIF for particular ith predictor variable as 1 upon 1 minus r xi का whole r square. This is the r square that we get. So if you calculate 1 upon 1 minus r square for that particular ith predictor variables, you will get कि उस particular predictor variables का VIF कितना है और variance inflation factor कितना है. अब यहाँ पे आप क्या करोगे, सारे predictor variables को ऐसे ही एक एक करके पहले x1 को लो, फिर x2 को लो, फिर ऐसे सारे को लेकर आप कैलकुलेट करो और सबका VIF कैलकुलेट करो. देन व्हेन यू विल कैलकुलेट द VIF, अगर VIF 5 या 10 से ज्यादा होता है, इट मींस दैट कि that particular ith और jth whatever you want to say, that particular variables indicates that कि इसका जो भी regression coefficient है, it is poorly estimated because of multicollinearity. अगर इसका let's say x1 का हम कैलकुलेट किया और इसका जो VIF आया, let's say it is 8, it means that it is greater than 5. It means that it has its coefficient poorly estimated due to the multicollinearity. So this, if you get this particular thing, you can say that there is a effect of multicollinearity on the data, and that particular variable xi जिसके लिए 8 आया है वो बहुत ज्यादा इफेक्ट हो रहा है उस पर्टिकुलर चीज से. So once you identify for all the predictor variables, let's say आपने आइडेंटिफाई कर लिया कि अच्छा आपका ये x2 x5 ये सब है जो इफेक्ट हो रहे हैं, then one natural question is what to do. क्या हम उन सारे predictor variables को रिमूव कर दें? Let's say आपके पास 3 predictor variables है, x1 x3 x5, और let's say x1 x3 मिलके x5 को predict कर रहे हैं और x5 poorly estimate हो रहा है, then what do you need to do? आप वहां पे x1 x3 को इग्नोर कर दोगे? So one natural question is yes, इग्नोर कर सकते हैं, but the thing is that you are going to lose some information. So आप अगर आप x1 x3 को हटा दोगे, बस x5 के बेसिस पे प्रेडिक्ट करोगे, still you will get some prediction for your original y, but वहां पे क्या होगा कि you are going to lose some information. So we will see like how to handle the variance inflation like multicollinearity, but I think the idea behind VIF is clear कि कैसे हम लोग
If I
VIF को
can
कैलकुलेट करते हैं.
summarize this, so basically for every x variable, so for xi, we just regress it over all the other x's. So we treat xi as our new y, and all the other x variables as the new as the new input data, and we regress it and find all the coefficients, and we find the r square for this for every xi, and we find the VIF from that r square, and we put a filter on VIF if it is greater than 5 or 10 for so for one or more one or more x variables, then there is multicollinearity.
Yeah.
Is that right?
So so one natural question is one can ask कि यहाँ पे हम filter 5 और 10 का क्यों ले रहे हैं? So let me just give you the basic intuition. So let's say VIF is equal to 5, okay, then 1 upon 1 minus r square is what is going to be. So this is going to be 1 minus 1 r square is going to be 1 upon 5, okay, then your r square is going to be 4 upon 5, right,
80,
which is equal to
80%.
0.8. So it means that your r square is means very high, 80%. Similarly, you can go for the and calculate for the 10, it is going to be 0.9 or something like that. Okay, so that is what it means. अगर आपका r square अगर x1 के लिए हम कैलकुलेट कर रहे हैं, लेट्स से सारे मिलके इसको r square 80 मिल रहा है, इसका मतलब सारे मिलके r इसको 80% ऑफ वेरिएबिलिटी जो x1 का है वो ये सब मिलके एक्सप्लेन कर सकते हैं. इसका मतलब कि इसका मतलब ये है कि आप x1 को हटा सकते हो, बट इट मींस दैट यू आर गोइंग टू लूज दैट 20% इंफॉर्मेशन दैट you may have got when you have kept x1, but वहां पे आप रखोगे तो multi-quantity हो जाएगी. Then what is the solution?
Also,
Yeah.
to find out like which all variables can combine to make x1, you can again do that p-value thing, right?
Yeah, definitely,
Uh,
definitely. Yeah. So यहाँ पे if you go on very high, deep analysis, let's say हम x1 को fit किए, and let's say x2, x5, once x2, x3, x4, x5, let's say x6 तक variable है आपके पास, and let's say out of those these are significant. So these have the major impact. But thing is that we can identify these things, but removing those things from the analysis would be a very tough choice, because certain amount of information we can always going to lose. So how to deal with the multi-quantity then? So there are first of all, we can use ridge regression, lasso regression, or principal component regression. There's some other method called elastic net regression. So that is the actually combinations of ridge and lasso. So we can utilize all those things to actually handle the multi-quantity. So principal component regression actually requires us to understand what is PCA, and I think that is a one of the concept in its own. So I will just explain a basic fundamental behind the PCR, like how to do principal component regression, and then explain region lasso in the detail. So principal component analysis, what we do, let's say हमारे पास x1 to xp predictor variables हैं. So we apply PCA on this particular thing, and let's say we get xPCA 1, xPCA 2. So these are all the principal component that we have got after applying the principal component analysis. So हमारे पास P component आएंगे. So this, when you apply a principal component analysis, whatever the coefficient that you get, these are orthogonal. Orthogonal means they are linearly independent. So linearly independent का मतलब ही हुआ कि they are not dependent. So there is no any multi-quantity within them. So they are each of these principal component are linearly independent.
so if
So that,
anyone does not know what PCA means, we'll do a separate session on it.
yeah. So
But
PCA
yeah.
PCA in its own is a separate concept, and it has very wide applicability in I think machine learning. So once you do the PCA का बस ये समझो कि आउटपुट हमें जो मिलेगा वो principal component मिलेंगे, which is again will be just like the x, but these are the principal component you have got from the PCA. So अगर आप इन पे मॉडल फिटिंग करोगे तो वहां पे जो आपका मल्टी क्वांटिटी का प्रॉब्लम है वो नहीं होगा, क्योंकि these are linearly independent and this is how this component are. तो लेटेस्ट सपोज आपने वहां पे मॉडल फिट किया, देन वहां पे आपको क्या करना है कि जो भी इनमें से इनसिग्निफिकेंट है बेस्ड ऑन द पी वैल्यू, जस्ट उनको आप रिमूव कर दो, और जो भी आपके बच गए आप उनको फाइनल मॉडल में ले सकते हो. So this is just a very crisp idea about how do you apply principal component regression. But हाँ, उसके लिए आपको principal component लगा के आपको components find करने पड़ेंगे. One more idea is to, let's say कि I think that is will be discussed in the principal component thing, the amount of variability that the variables can explain.
Yeah, so that we calculate using the eigenvalues. So we can
Eigenvalue
take
and
it
yeah
separately. Yeah.
So the overall idea is once you find the principal component, आप रिग्रेशन लगाओ, सिंपल जो आप रिग्रेशन मेथड लगा रहे थे उसमें से जो जो सिग्निफिकेंट नहीं है, लेट्स से ये नहीं है, वो उनको आप डिलीट कर दो, बाकी जो वेरिएबल बच गए आप उनको लेके आगे बढ़ सकते हो. बट द थिंग इज दैट यहाँ पे आपने वेरिएबल्स को ट्रांसफॉर्म कर दिया, लाइक लेट्स से वांट टू हैव द ओरिजिनल वेरिएबल्स इन द पिक्चर, देन हाउ वी आर गोइंग टू डू दैट. लेट्स से अगर आप एज ले रहे हो, जेंडर ले रहे हो और इनकम ले रहे हो, देन यू वांट टू सी कि एज का क्या इफेक्ट है. दोज अगर आप प्रिंसिपल कंपोनेंट में अगर लेट से आप एक्स पीसीए 1 लेते हो तो इसमें सारे वेरिएबल्स का इंफॉर्मेशन घुसा हुआ है. इट्स नॉट लाइक यू कैन सेपरेट आउट एज एंड जेंडर फ्रॉम दिस पर्टिकुलर थिंग. So that is why we have a method called ridge and lasso. So just let me give you the basic introduction of ridge and lasso, then we will go into detailed explanation. So हमें पता है कि like in the basic classes I told you we were actually trying to minimize this error term. Like I told you we have a line. So हम लोग क्या करते हैं कि we have a method of least square जहाँ पे we have the point, original point, and we have the predicted point, and we calculate the error and we try to minimize this sum of the squared error. So this is what the sum of the squared errors looks like, right? Yi minus y hat, and this is what your y hat is, right? So ridge में क्या करते हैं हम लोग कि ridge में we have some different constraint. लाइसो में वी हैव डिफरेंट कंस्ट्रेंट. सो रिज का मतलब ये भी होता है L2 norm एंड लाइसो का मतलब होता है L1 norm. सो ये जो नॉर्म वाला जो टर्म है ना, ये आया एक्चुअली रियल एनालिसिस से. इन द रियल एनालिसिस वी हैव on L1 norm, L2 norm, LP norm, L infinity norm. So this is what L1 norms looks like. यहाँ पे हम लोग क्या करते हैं कि जब आप ओरिजिनल क्वांटिटी को मिनिमाइज कर रहे हो, दिस इज व्हाट वी वर डूइंग इन द रिग्रेशन. तो वहां पे आप एक कंस्टेंट लगा दो. कंस्टेंट क्या है कि ये जो बीटा जे है ना, this particular thing and this particular sum is going to be less than a particular quantity s. तो जब आप यहाँ पे कंस्टेंट लगा दिए ना, तो मैं बोला ना कि बीटा जे क्या होता है मल्टीप्लिकेटिव, दिस बीटा जे इज गोइंग टू बी वेरी लार्ज. तो यहाँ पे बीटा जे पे कंस्टेंट लग गया. दिस बीटा जे इज कैन नॉट गो लाइक दिस कंबाइंड बीटा जे कैन नॉट गो बियॉन्ड दिस पर्टिकुलर कंस्टेंट. सो दिस इज व्हाट हेल्प्स यू इन हैंडलिंग द मल्टीप्लिकेटिव. वहां पे बीटा जे बहुत बड़ा नंबर नहीं हो पाएगा बिकॉज यू पुट अ कांस्टेंट. एंड रिज में क्या करते हैं हम लोग, एक कांस्टेंट लगाते हैं, बट दिस कांस्टेंट इज डिफरेंट फ्रॉम द लाइसो. यहाँ पे हम लोग क्या करते हैं, यहाँ पे बीटा जे स्क्वायर का जो समेशन है, सॉरी जो समेशन है वो लेस देन इक्वल टू सर्टेन क्वांटिटी होता है. सो दिस पर्टिकुलर क्वांटिटी विल हेल्प यू in handling the multiplicativity. How it helps you? It helps because this particular estimate won't go beyond this summation. Like this summation, अगर आप let's say beta 1 is equal to 5 है, beta 2 is equal to 7 है, और 5 square plus 7 square, let's say 25 plus 49 is going to be some quantity. And let's say you put here 30. तो अगर आप 30 यहाँ पे रखते हो तो ये क्वांटिटी बहुत बड़ा हो गया ना, तो ये बीटा जे इसके पार नहीं जा सकता. यू हैव पुट सम कंस्टेंट. सो the model will try to minimize beta j in such a manner that this constant holds, and once this constant hold, this will not be a very large number. So I
So
think basic idea about, yeah.
do we need to separately apply these constraints, or will that uh, minimizing term, like this summation of that beta j xij, will that only ensure that constraint?
So what we do, so the constant that we have here, so when we go for applying like maximum minima, so maximum minima means that कि हम जब minimize करने जाते हैं, तो if you just go into the deep of the mathematics, we use a Lagrange multiplier. So there is a called a Lagrange theorem. What we do, let's say you have a function f1 that want to maximize under constant of f2, so we just can write f1 plus lambda f2, and you can minimize these particular things together. So वहां पे हम लोग क्या करते हैं कि when you will try to go implement ridge regression in the Python, you will have this lambda thing. तो ये lambda thing कहाँ से आया, क्योंकि ये जो constant है हमारा, it was less than equal to x. So हमने इन दोनों को मिला के using the Lagrange multiplier एक simple equation बना दिया, single equation. अब हम इसको मिनिमाइज करेंगे. तो लेट्स से अब हम इसको जब मिनिमाइज करेंगे तो आप इसको डिफरेंशिएट करोगे तो एक लैम्डा का पैरामीटर हमेशा रहेगा. सो जब आप रिज रिग्रेशन फिट करते हो तो वहां पे एक लैम्डा आपको चूज करना होता है, whether the lambda is 1 2 what. अगर लैम्डा आप 0 लोगे, you can see that it is again going to be the your original linear regression, right? So this is called a tuning parameter. And similarly for the lasso regression also, you can see here we have a lambda, and this is also called a tuning parameter. So ये इक्वेशन हमने कैसे बनाया, ये हमने बनाया एक मैथमेटिक्स में होता है Lagrange multiplier. So if you read the optimization of f1 based on the constant of f2, so basically we write optimize f1 plus lambda f2. This is called Lagrange coefficient. So this is what that particular coefficient is, that we have a hyperparameter here. Hyperparameter means that we have to choose the value of lambda, and based on the value of lambda you will have different results for this. Obviously for lambda is equal to 0, this is again going to be the simple linear regression, sorry, multiple linear regression. So I think the basic idea about how do we apply Ridge and lasso and why these are able to constraint betas is clear, because once we have the constraint of less than equal to s, this estimate won't go beyond this particular overall quantity.
So this has to be for at least for lasso, this has to be minimized using gradient descent, right?
Yeah, means
because it's not differentiable.
Yeah, for lasso it has to be go for gradient descent, but for this sorry, for this particular thing you can calculate a ridge regression, and this come to be x transpose x plus lambda ip inverse x transpose y. So this is the beta hat for the ridge if we just estimate. So this lambda ip I is actually the unit matrix, like 1 1 1 in the, what you can say, in the
Diagonal.
diagonal, and all are 0, and this x transpose x is the original we have. So you can see that x transpose x का inverse नहीं exist करता था, but this quantity is different from x transpose x, and this inverse will definitely going to exist.
Can there be a chance that this inverse does not also exist?
It's highly unlikely, because अगर हम लोग थोड़ा geometric meaning पे जाएंगे, तो we also know that we have put this particular constant. So this constant less than equal to s ensure that this quantity does not go like equal a very large number. So this means this constant is the basic intuition behind. Let me give you. Yeah, this constant is the basic intuition behind this thing should work, because intuitively we can say that betas are not going to very large number because of this constant. So based on that we can say that this can be. So वहां पे होता है, अगर आप let's say take lambda, like I told you कि lambda की वैल्यू जो है, अगर आप very very small ले लेते हो close to 0, then again it's going to be problem, because this lambda ip again is going to be something called zero matrix. Then again it's like x transpose x inverse x transpose y. तो वहां पे you have to like experiment with different value of lambda, whatever you find, but try to not pick very large lambda, like let's say pick lambda is equal to infinity. तो अगर आप lambda equal to infinity ले लोगे, तो it's just like कि आप बहुत ज्यादा वहां
Or
पे
every beta will be very small then.
So this
So
is what
we have a question.
it's, yeah.
S is a function of lambda. What is
S is not
S?
a function of lambda. S is just a number, like it's a real number. Lambda is what we have is we use when we try to minimize this particular term. So
Okay, this
अगर
is
आप
okay.
हाँ, so let's say ये f1 हम इसको मान लेते हैं, ये f2 मान लेते हैं. तो अगर आप f1 को minimize कर रहे हो, because this is the constant, so f1 plus lambda f2, this is where the lambda comes. This is called Lagrange multiplier. Okay, so this is called constant optimization. So if you'll just go and read more about the constant optimization, you will come up with these things. And वहाँ पे Lagrange is the very like a common algorithm. आप कोई भी एक दूसरा एल्गोरिथम लिखा रहेगा, एक्स स्क्वायर प्लस 2x प्लस 1 अंडर द कांस्टेंट दैट 3x स्क्वायर प्लस 1 इज लेस देन 2. सो कुछ भी हो सकता है वहां पे. इट्स नॉट लाइक anything, it can be anything else. So whatever you are looking at right now is a very basic implementation of Lagrange multiplier. So these are the constant. The s is just a number, it's not a some, it's a hyperparameter actually. It's hyperparameter means that ki based on different s you will get different betas.
Also, can we also have different lambdas for different betas, or is it standard to have the same lambda for every beta?
No. You can have different like this lambda is a single quantity. Like we have to pick a single lambda, and
Yeah,
based on that,
but can
this
we
particular
have
thing.
lambda I as well for every beta?
Okay, so this particular thing is escalated, like ridge and lasso regression is escalated later. So this particular thing is called elastic net. So elastic net में क्या होता है कि हम ridge का भी एक पैरामीटर यूज करते हैं और एक lasso का भी यूज करते हैं. तो ridge के लिए let's say we are using lambda 1 and lasso के लिए let's say we are using lambda 2. So RSS plus lambda 1 ridge का पैरामीटर, मतलब ridge का वो जो constant है वो, plus lambda 2 lasso का constant है वो. So this we can use, but yeah, for whole ridge this lambda should be equal. And this is because यहाँ पे देख सकते हो आप कि s जो है यहाँ पे हम combined उसके ले रहे हैं. अगर यहाँ पे हम इंडिविजुअल कोफिशिएंट के लिए s डिफरेंट ले, लेट्स से बीटा 1 मॉड बीटा 1 लेस देन इक्वल टू 4 मॉड बीटा 2 लेस देन इक्वल टू 5, तो ये entirely it's a new thing, and actually someone need to explore these areas. So yeah, this is a very nice question. Yeah, this can also be a nice thing to explore.
Also, I don't think any library supports this as of now.
Yeah, no, these are all I think first of all we have the libraries for the simple single lambda, but for these और इसको इंटरप्रेट करना इज लाइक ऑल्सो लेट्स से कि हम कोई एक्सपेरिमेंट कर रहे हैं, लेट्स से वी आर डूइंग एनी एक्सपेरिमेंट इन फिजिक्स और एस्ट्रोनॉमी, वहां पे हम पता है कि जो पर्टिकुलर कोफिशिएंट है वो इसके बाहर नहीं जा सकता. सो वी कैन अप्लाई दिस काइंड ऑफ कांस्टेंट, बट या फॉर दैट हम उसको ऑप्टिमाइज करने के लिए जो हमारा ग्रेडियंट डिसेंट है जो एल्गोरिथम होगा, इट विल वर्क entirely on this concept, and इसको भी यूज करना पड़ेगा उधर.
Also, if we want to punish some beta more than the others, we can have a larger lambda for that.
Yeah. So one final concept is like how do we interpret region less, और हमें क्या यूज करना चाहिए. So let me give a very basic information about region less. तो जब आप रिज रिग्रेशन अप्लाई करोगे तो आपका जो बीटाज है, लाइक बीटा जे बीटा वन जो भी है, वो कंस्टेंट होगा, बट सेट एनी बीटा इज इक्वल टू जीरो. मतलब यहाँ पे अगर आप बीटा वन टू बीटा यूज कर रहे हो तो सारे का एस्टिमेट आपको मिले, कोई जीरो नहीं होगा. बट अगर आप लैसो यूज कर रहे हो तो इट इज ऑल्सो कॉल्ड पैरामीटर श्रिंकेज मेथड, और यहाँ पे कुछ वेरिएबल्स होंगे ऑटोमेटिकली जीरो हो जाएंगे. तो वो जीरो कैसे हो जाता है, तो उससे पहले आप ये समझ लो कि अगर आप ऐसा कुछ इक्वेशन यूज करना चाहते हो जहां पे आप नहीं चाहते हो कि कोई भी आपका वेरिएबल लूज हो, वहां पे आप रिज रिग्रेशन यूज कर सकते हो मल्टीप्लिसिटी हैंडल करने के लिए. बट लेट से आपके पास 100 या फिर 500 वेरिएबल्स हैं, और आप चाहते हो कि मैं इसको थोड़ा मॉडल को सिंप्लीफाई करूं और थोड़ा मल्टीप्लिसिटी भी हैंडल हो जाए. In that particular case, you can use lasso because lasso will set some of the variables equal to zero. So one natural question is कि lasso कुछ कुछ variables को zero कैसे कर देता है, like how this particular things happen. So let me explain it with the right hand side graph. तो यहाँ पे लेट्स फर्स्ट अंडरस्टैंड कि अगर हम लोग अप्लाई करें लैसो रिग्रेशन टू डायमेंशनल के केस में तो हमारा कंस्टेंट क्या होगा. और कंस्टेंट विल बी सिग्मा आई फ्रॉम 1 to 2 बीटा आई समेशन लेस देन इक्वल टू सम सी और एस. दिस इज इक्विवेलेंट टू मॉड बीटा वन प्लस मॉड बीटा टू लेस देन इक्वल टू सी. तो यहाँ पे जब आप इस ग्राफ को प्लॉट करोगे, इस इज गोइंग टू बी दिस पर्टिकुलर ग्राफ. तो यहाँ पे जो ब्लू शेडेड रीजन है, दीज आर योर पॉइंट ऑफ इंटरेस्ट बिकॉज दिस इज लेस देन इक्वल टू सम कांस्टेंट सी. उसी तरह अगर आप रिज रिग्रेशन का प्लॉट करोगे तो दिस इज इक्वल टू बीटा वन स्क्वायर प्लस बीटा टू स्क्वायर इज लेस देन इक्वल टू सी स्क्वायर, राइट. सो वहां पे क्या होगा कि जब आप इसको प्लॉट करोगे दिस विल बी इक्विवेलेंट टू अ सर्कल. सर्कल मींस ये जो शेडेड पॉइंट है, दिस इज ऑफ आवर इंटरेस्ट. तो जब हम यहाँ पे फाइंड करने की कोशिश कर रहे हैं कि हमारा एस्टिमेट जो रिग्रेशन का होना चाहिए वो अंडर द कंस्टेंट, लाइक अगर लैसो का हम बात करें तो हमारा कंस्टेंट क्या है, दैट इज सिग्मा आई फ्रॉम 1 to 2, लेट्स से 2 मॉड बीटा आई लेस देन इक्वल टू सी. तो हमारा जो estimate होने वाला है, that estimate has to be within this constant. So that estimate will exist when this, let's say this is the beta 1 and this is the beta 2 because we have plotted this graph. तो इस जो आप यहाँ पे सर्कुलर पट्टी देख रहे हो, this particular circular things, this will be the one of the estimate. Like estimate यहाँ पे हो सकता है, यहाँ पे कहीं भी हो सकता है. But this estimate will exist under this constant when this will exactly what you can say cross or touch the boundary of this particular graph. दिस पर्टिकुलर ग्राफ. सिमिलरली अगर आप रीच की बात करोगे तो ये तभी एग्जिस्ट करेगा जब इस पर्टिकुलर ग्राफ की बात करोगे इसमें टच करेगा. तो रीच रिग्रेशन में क्या होता है कि ये सर्कुलर है, देन वी विल हैव टचिंग ऑन द सर्कुलर बाउंड्री. यहाँ पे कहीं सर्कुलर बाउंड्री पे टच कर रहा होगा तो वहां पे आप देख सकते हो कि सर्कुलर बाउंड्री पे कुछ ना कुछ वैल्यू मिलेगी आपको उस पर्टिकुलर बीटा वन बीटा टू की. बट ये लैसो केस में क्या होता है
what
कि
exactly is this circle or ellipse?
दिस इलिप्स आर द आइडियल.
I think we lost you. Hello.
वन हैट और बीटा टू हैट जो हमारा एस्टिमेट है, तो ये सर्कल
I
वही है कि
think
इस
I think I
पर्टिकुलर.
lost you. I think I lost your voice. Can you repeat?
हेलो.
Yeah, I can hear you now.
So I'm telling that this particular betas are those values of like this beta 1 hat and beta 2 hat are those particular values beta that we want to estimate. Like we have beta is equal to x transpose x inverse. So अगर हम सारे betas की बात करते हैं टू डायमेंशनल स्पेस में, लेट्स से हमारे पास beta 1 है beta 2 है, तो ही
So
वेरिएबल्स
we
हमारे
only
पास.
have two variables. Okay.
हाँ, लेट्स से मींस फॉर सेक ऑफ सिंप्लिसिटी.
Yeah.
सो यहाँ पे
Yeah.
हमारा जो एस्टिमेट है इसी कहीं स्पेस में कहीं ना कहीं एग्जिस्ट कर रहा होगा कहीं भी, लेट्स से
Hmm.
एनीवेयर. एंड वी आल्सो नो दैट कि this particular
So it can be any point in this plane, right? Not so there's no need for ellipse or circle
yeah,
here,
there
right?
is need because
Yeah.
we know that कि our y minus beta naught minus beta 1 x1 minus beta 2 x2 का whole square, this particular thing we want to minimize. So if you want to plot this particular thing and means अगर जब आप सिंप्लीफाई करोगे तो आपको मतलब ये एरिया जो है वो एक
Okay, this is an ellipse. Okay, got it.
सो वहां पे हमारे पास कंस्टेंट है कि जो 1 मिनट, वहां पे हमारे पास कंस्टेंट है कि वहां पे हमारे पास कंस्टेंट है कि जो रिज रिग्रेशन में पॉइंट होगा दैट शुड बी मॉड बीटा 1 प्लस मॉड बीटा 2 लेस देन इक्वल टू सम कांस्टेंट c. So वो तभी एग्जिस्ट
Hmm.
करेगा जब ये दोनों कर्व एक दूसरे को टच करेंगे उस पॉइंट पे, राइट?
Do they need to touch or they can cross also?
क्रॉस ऑल्सो, बट मतलब जहां पे वी हैव अ टच थिंग, आई थिंक दैट वुड बी
There we can
द
stop
फर्स्ट
the
पॉइंट.
gradient
या
descent.
क्योंकि
Hmm.
अगर आप ग्रेडियंट डिस्टेंस मिनिमाइज करो तो जैसे ही आपको
Hmm.
फर्स्ट चीज वो सेटिस्फाई होगा, दैट विल गिव यू द रिजल्ट. सो
Hmm.
आई सो द बेसिक थिंग इज कि इलिप्स पे तो ये जो रिज रिग्रेशन है वहां पे इट विल टच ऑन द सम दिस सर्कुलर सरफेस समवेयर, but this particular thing on the lasso case it will touch somewhere in the axis. So one may ask you why axis. So just give me कि अगर यहाँ पे ये हमें अगर यहाँ पे काइट बनाना होता तो we should have drawn this. So हम देख सकते हैं कि ये जो बाउंड्री है it will touch surface first then will touch any axis. तो यहाँ पे तो axis का कोई सवाल ही नहीं है. So it will touch this surface rather than touching some axis at random, right? Because this surface have more area in general.
So like
So
there's
when,
more chance to
yeah, more chance,
uh,
yeah, this is just what I want
hmm.
to take. This is more chance to touch on the surface of circle rather than touching it on the corner. Or
Hmm.
here we have more chance to touch on the axis rather than touching on any surface, because alternatively these are pointing outwards, right?
Uh, no, this isn't very clear.
Uh, so other way to explain is okay, so other way to explain is let's understand as if this particular ellipse like shape touch on the axis, then this is going to set that particular coefficient into zero. तो अगर यहाँ पे टच करता है तो यहाँ पे
Yeah.
हमें एक पर्टिकुलर कोफिशिएंट जीरो मिलेगा, अदरवाइज दूसरा के
Yes.
कुछ में वैल्यू मिलेगी. बट अगर हम इसको इन जनरल पी डायमेंशन में बात करें तो लेट्स से किसी पर्टिकुलर एक्सिस पे टच कर रहा होगा, तो वहां पे हमें जैसे लेट्स से अगर एक्स वाई जेड की हम बात कर रहे हैं, ठीक है, let's say
Hmm.
it touches this particular thing into some axis, not a particular plane, but yeah, that will not be the line, that will be some plane, right? That will be some plane.
Yeah.
So
Yeah.
if it's touch in the xy plane तो वहां पे z जीरो होगा, अगर yz प्लेन में करेगा
Hmm.
तो x जीरो होगा. इसी तरह अगर p डायमेंशन की हम बात करें, लेट्स से टच ऑन सम पर्टिकुलर हाइपर प्लेन, तो वहां पे कुछ कुछ कोफिशिएंट जीरो हमें मिल जाएंगे, राइट?
Hmm. Hmm.
But that is how the lasso actually does the parameter shrinkage thing. I think this visualization will be more clear when we will actually be able to visualize this particular shape in multi-dimension rather than uh,
Hmm.
two-dimension. But
Also,
yeah, the basic, yeah.
I think the points inside the square. I think in within the square there are like an infinite more points. I think
Mhm.
uh, the regression will also explore in that and to minimize the function even more, right?
Uh,
Unless there is a like a extrema on the surface.
It's right, but I think that comes more from the constant. Like we have put like a summation of I from 1 to n, summation beta I less than equal to s. So this equal to constant actually.
I think if we look at it like from the equations, I think it might be more clear, but I think let's move ahead for now.
Yeah. Anyway, I think this is basic intuition, but yeah, if you just read more about this, so this ISLR book have some content on this, not much, but yeah, the same picture has been taken from that particular books only. So if you just read that particular book, you will have some more intuition about it. So
Yeah.
overall, whenever you want to use the method to actually have some parameters linkage, or you can say that you want that if you have 10 variables, you want only 5 variables. So let's say you want some less number of variables. वहाँ पे you can use lasso. Otherwise, let's say you don't want to use any variables in the regression, you have to use ridge regression. So like people ask, ridge is better or the lasso is better? So this actually depends on situation कि what you want to do. अगर आपका aim है कि model को simplify करना, then lasso is better. But your aim is that कि you don't want to lose any information, then I think Reach is better rather than Lasso, because it will certainly going to lose some information.
Yeah.
So let me give you a certain idea about how to implement this BIF code. Let me stop sharing the screen. So here you can see that in the variance inflation factor, we have a variance inflation factor variables inside a particular stat models library. तो यहाँ पे if we'll go inside stat models dot stat dot outlier influence, here we have the variance inflation factor. So what we will do, we will try to calculate the variance inflation factor for each and every variables. So we have these significant variables in our model, like we saw. So just let's calculate variance inflation factor for all these things. So when you calculate the variance inflation factor and just have a basic data frame for this, you can say that this age and this BMI has this BIF of greater than 5. So you can assume that this age and BMI are actually getting affected a little through, or you can say that by multi-quantity effect. So these two variables are actually being affected. So what you can do, just once you have this thing, obviously there are some methods to actually remove the variable, see the analysis. But nonetheless, what you can do, you can apply region lasso. So the basic idea to apply region lasso is to just import from the sklearn library. So this stat models library also have a region lasso, but that is more complicated to understand, and that is not a straightforward very, because we have to set the parameters, write some more lines of code for them to understand, and it is a very good idea to explore that. But simplicity, you can import and less. What you can do, you can fit your model, and once you fit, you can read the coefficient of the region lasso. So just let's see here. You can see in the lasso we have not got any coefficient 0, because I told you it will some coefficient to 0 does not mean that it's actually going to set some coefficient to 0 always. Like we told, this has high probability. Sorry, this has very high probability to cross at this particular area rather than this area. But yeah, it does not mean that it will always cross this particular thing, this beta j. So that is why we can get different value of coefficient, and when we change lambda based on that alpha, or may say alpha here, if you change this particular alpha which is equal to lambda here actually, then you may get a different coefficient here, like we may get 3 coefficient or 2 coefficient, something like that. So once we implement this, we can see that the estimate that we have got for this particular thing is actually different for the estimate. Like this age has estimate of 259, but if you go to your original model, you can say that your has age has the coefficient of 260. So some coefficient will always be vary rather from your original model. So this is what the impact they have, and you also discussed, because we are putting some constant, and based on the different alpha, you will be able to get you will able to get different estimate of this coefficient. In fact, this coefficient also differ in terms of region lasso, right? And one major idea is to first check for a lot of value of alpha, that we also do hyperparameter tuning. So that is, I think, entirely other thing in terms of how do we implement a real life model in the regression or anything. So we do hyperparameter tuning, in which we find an optimal value of alpha for which our R square, adjusted R square, is better than other alphas. So we may do that first, and then we apply a value of alpha for which we get the best result. So this is how we can implement region lasso on the Python.
Can we also do the p-value tests after bridge or lasso?
We can, but I think for that we need to go through the stat models API library. But
Hmm.
but the thing is that we are actually applying this particular thing on the significant variable. So their estimate are going to be affected a little bit. Their standard is going to be affected, but overall your model is going to be significant. Like once one thing you can say that कि अगर हम PCA apply करते हैं, so let's say we have XPCA 1, XPCA 2, something like that. So rather than अगर ये सब आपस में correlated नहीं भी है, then also we can have some variables as insignificant. So in that case we may remove those variables also. So यहाँ पे ये है कि like all those variables are significant, but after applying Regression PCA, it may happen that some variables may become insignificant because anyway the standard deviation is changing. But yeah, for that also we need to either go through the stat models API library, or we also do hypothesis testing. Like ये इसके learn में तो नहीं है ये hypothesis testing का फंडा. It is
Maybe we
only in the stat
can
models
check
library.
the source code in stat models and make our own
Stat models
make our
may
own
we
function.
have, yeah, stat models we have. The only thing is that is slightly complex. Like right now there are different terms actually that people won't able to interpret at this point. But yeah, the whole idea is to this coefficient will change. This is what I want to do. This coefficient will change because this is what I told you. We have the constant like sigma I from 1 to p. This beta j is less than or equal to some s. So this is what we had initially. So this for the lasso and for the ridge we have a square. So that is why this coefficient will change because these are setting some constant. And one ideal way is to like calculate for different value of alpha and see whether and also see the like r square divided r square and how the particular thing is actually behaving in the different types of alpha. I think
Great.
we have
So I
seen
think
this.
we are done with the master class. So everyone, I have put in a form in the chat. So in case you have attended all the 3 sessions of this master class, you can fill up this form to get the refund via UPI. So yeah, I think that's it, Nitin.
Yeah, we can also share a feedback form for them so that they can fill the
Yeah.
feedback form like how and what. Like we had this for this session as a first session itself. So I know we also need to do a lot of improvements for our future session. So maybe we can have a little bit of more material with the respect of code or theory itself. But yeah, whatever the feedback is, we will definitely take it as a positive thing and we will try to improve.
Yeah, so I'll send out the feedback form via email to everyone who have attended any of the sessions. So I think that's it for today. Any questions, anyone?
Okay, then
think
I
we can
think
wrap up.
yeah.
Yeah.
Thank you guys for
So
joining for all the 3 days.
yeah, thanks
It's really
everyone.
nice.
Fill up the form. Save the form link because this meet is going to end.
Yeah.
All right. Thanks, Nitin.
Thank
Yeah.
you. Thank
Thanks.
you. I said for the
Bye.
cooperation. Thank you. Guys, we will have some more session in the future. Just connected with us on the LinkedIn. You will get to know.
Yeah, please feel free to connect with us on LinkedIn. Nitin, can you put your LinkedIn profile
Yeah.
link in the
Yeah,
chat?
definitely. Just give me a.
I'll also put mine.
Yeah. Yeah.
Yeah,
Thank you,
so these
everyone.
are our LinkedIn profiles. Feel free to connect with us and message us if you need anything. And thanks, Nitin, for this masterclass. And we'll come up with some other masterclass soon.
Thank you. Thank you, everyone.
Thanks. Bye.